We would like to demonstrate the Formally Safe Routing or FSR Analysis and Implementation Toolkit. This provides a common framework for describing routing protocols in a declarative manner, for analyzing those protocols for safety properties, and for running them on real network configurations. In this video, we'll show off the capabilities of FSR by means of one example. In the full demo, there'll be many different examples showing a wide range of features. Using network data log, we can write a concise declarative specification of the basic path vector mechanism, and here it is. Rule M1 is telling us how we import routes from our neighbors. Rule B1 shows how those imported routes can be installed in the local routing table, and then Rule L1 is choosing the best route out of that table. Finally, in Rule N2, we see how permitted routes to export can be distributed to our neighbors. So that was the mechanism, and what about the policy? Well, in this example, we're going to choose routes according to the Gower-Rexford economic criteria, and if those are insufficient to find a single best route, we're going to break ties using the AS-level hop count. Here, the Gower-Rexford pref function is saying that a customer route expressed by C will always be preferred to a peer route R, or equally to a provider route P, but there's no preference here between peer and provider routes. Some policy is also expressed in the Gower-Rexford export function, which restricts the set of routes which are able to be distributed to our neighbors. For example, in the fourth clause here, we see that a peer route can't be told to another peer. The hop count attribute is much simpler. We just add up the path length and we prefer shorter paths. And in fact, there are a great many possibilities for different policies that could be expressed instead of these, as we'll see in the real demo. Using the declarative networking engine, we can compile this network data log specification into code that will run on the NS3 network simulator. Let's see a replay of that execution. In this example, we have 40 autonomous systems arranged into 3 customer-provider hierarchies. There are also peering links within and between those hierarchies. In this diagram, peering links are shown horizontally. Customer-provider relationships are expressed vertically, with providers at the top and customers on the bottom. Let's stop here and look at the routing table for node 7. We can see here the different routes that it's learned to all of the destinations in the graph. For each of these, we can see the path that it's taking, as well as the generated signature in terms of our customer peer provider system and the hop count. For example, from node 7 to node 15, we can see this is a provider path P of length 3, going from node 7 to 1 to 13 to 15. However, the link to AS16 is a peer path of length 2, going from 7 to 14 to 16. Looking back at the diagram, we can see that 7 did not take the most direct path to node 15, which would be via node 14. Instead, it went 7 to 1 to 13 to 15. That's because node 14 was a peer of both 7 and 15, and in our policy we said that a peer path could not be given to another peer. However, for the path to 16, this is fine because 16 is a customer of 14. In this example, the routing configuration converged to a fixed solution, but perhaps something else might have happened if the signaling timings had been a little bit different. In order to find out whether that's true or not, we need to look at formal properties of the configuration, and we do this by means of the ESIS SMT solver. From the configuration, and from information gathered during the execution, we can find out all of the paths that might be learned by each node, and what their relationships must be formally in order for safety properties, such as strict monotonicity, to be verified. This property ensures that the configuration will definitely have a unique solution, if we can label the paths by numbers in such a way that the extension of a path always has a larger number than the original path, and for 2 paths from the same source to the same destination, if the least preferred path always has a larger number than a more preferred path. We can put all of these constraints into the SMT solver to see if there's some labeling of the paths that will satisfy all of these conditions at once. And we find out that in this case there is. But if all of these constraints couldn't be satisfied at once, then the tool would give us a minimal counterexample, the minimal unsatisfiable core of the contradicting constraints. A user can then use this information to refine their design. In the demo, we intend to show a variety of examples, both of instances that are safe and of ones which are unsafe, as described in the proposal.